So let me quickly get everything ready. Hopefully this works. Oh, of course, I forgot to check the microphone. Oh, yeah. Hopefully it works. Otherwise, I will cry. So hopefully you see back where we were. And now it's quite interesting to compare what we get from so basically the emission spectra from a disk-like spiral galaxy, and here emission spectra from a old or an elliptical galaxy. And here we see loads of hydrogen and only a bits of oxygen left or in here. And what we see here in elliptical galaxies, we see a lot of sodium and sulfur, magnesium, so heavier elements that we would typically associate with the burning of elements in lighter, medium, and maybe even heavy stars. Okay, well, the next thing is, so we get the chemical composition that elliptical galaxies are usually don't have too much hydrogen left relative towards these heavier elements. So there loads of hydrogen seems to have gone. And looking, for example, at this, if you remember, at this 21 centimeter line from atomic hydrogen, we get basically hydrogen gas distribution. This 21 centimeter line, this is nice. We can do this with the radio telescopes. So we have the loads, we have big ones. They're easy to operate because they are Earth-based. And then we can even look at nearby galaxies at the flow patterns. We look at an elliptical galaxy, what we often see is that the gas is driven out. While in other galaxies, like ours, or in disk-like, what means spiral galaxies or part spiral galaxies, we get here most of the gas recycled and often even an influx from the intergalactic medium. So that means they acquire even gas, while here obviously the elliptical galaxies seem to get rid of the few or a bit of gas that they still have left. That means it turns out that these galaxies are basically ceased to form stars. While obviously in the spiral galaxies, there's still the party going on. Okay, then the next thing that we can do is what is called differential rotation. So we look now at the velocity, how fast is the stuff here revolving around the center of the galaxy. We can again use the redshift to Doppler shift or blue shifted if it moves towards us, redshift if it moves away. So the Doppler shift of the light coming from the stars, so the hydrogen lines, and this Balmer series in the optical. Or further out, what we do is we use this 21 centimeter line again. And there the red or blue shift. So this 21 centimeter line with the proton is rotating, makes a spin, and the electron too. And if they are aligned, this is a bit energetically less, slightly less favored than if they are aligned. So, and if it flips from this aligned to this anti-aligned, what gets this 21 centimeter line emitted, which then can be used. So what gets then this rotational profile. Now it's worth to have a quick look. What would we expect? So let me see whether I find the tablet. Okay. Tablet software. So what we have is usual crap. I don't know, every time I close the tablet, somehow in the original software it changes the monitor. Okay. So, okay, so we have our galaxy, the spiral arm, two spiral arms, and now it's rotating. So is a given velocity. Given the distance towards the center, so this radius, we would expect now that the velocity is a function of this radius. So what would we expect? Well, we would have a force equilibrium between the gravitational force and the centrifugal force. And now we can look at the gravitational force, which was given for body of the mass m. Then obviously we have the mass of the stuff that attracts capital M. Then the gravitational force would be this Newton's gravitational constant. There's big M, small m divided by r squared. Okay. So if we are outside of the matter distribution, so just this hydrogen gas, we would expect something that's proportional to 1 over r squared, which is some parabolic behavior. And now in here, we have, of course, stuff that is pulling out here, the same we have here that's pulling. And we have stuff that is in the inner side. And if we say only the stuff in the inner side really counts, well, how much mass do we have in there? This is proportional to the volume inside. If we say it's proportional to the volume inside, then the mass is proportional to r to the power of 3. So entering this, we have g, r to the power of 3, m, r squared. So that would be then proportional to r in the inside. Just a straight curve. And of course, then here's some bend over region. So this is what we would expect. So I need to close this stuff and then hopefully back. Yeah. So this is our expected curve. But then, of course, we have to scale it up or down according to the amount of visible matter that we have. And now the observation is quite interesting because it starts with this basically proportional to the mass, but then it doesn't go over to this 1 over r squared. It still keeps on increasing this velocity, which means the outer stars are much too fast. They cannot be bound. They are so fast, if only this visible matter is here, they are not bound. They would spiral outwards into the nothing. Or our galaxy would quickly dissolve. That would be annoying, wouldn't it? No. Oops. Well, let's hope this here records everything, but it's anyway a short video, so I could repeat. Okay, so we get basically this. We see the stuff outside is too fast. Well, and who or what would this mean? Well, so the stuff, there must be more mass in the galaxy. And it must not only be here, where we can see it, otherwise we would get outside again this 1 over r squared behavior. It must be also distributed in a halo around. So, in fact, from this curve, one can determine that a galaxy must consist of 6 times more dark matter than it consists of baryonic or visible matter. Baryonic is basically the matter that interacts with light. Or for a long time, the neutrinos were the candidates. But in spite that there are so many around, they are too light. They cannot make up for this dark matter. So and they are they are so light, they are too fast. They would make these clumps that we have in the cosmic microwave background. Observed was this stuff by Fritz Zwicky. Remember the guy with the neutron stars that like to have a good argument with everybody, and the great dame of astronomy, Vera Rubin. She was the lady that convinced the US Congress to invest this couple of billions into the Hubble Space Telescope. Okay, so they basically came up, and therefore also some of the first people to propose dark matter. So we can now again look at the observed curve, and if one has a spheroid, so somewhere at the center, just a bulk, so this is the sphere. Then one has this disk around the blue stuff, but this would basically explain. This would be nicely, this is rho is m proportional to distance, and they go 1 over r squared. So one needs this halo to go really for this observed stuff. And now, what does the halo consist of? Of course, it's dark matter. And then we get this picture. We have our disk of the spirals. We have somewhere a bulge in the center. This is the luminous matter. This is surrounded by so-called globular clusters. Globular clusters are islands of stars with maybe a couple of 100,000 to maybe 1 million. They are like droplets in spherical shape, and they surround galaxies. Many of them. We will later come back to the ones of our Milky Way again. And they are the big problem of this Bolshoi simulation. It's very successful, so one expects that it could reproduce them. And it predicts some, but all in the plane of the spiral, not above and beyond. Obviously, it has problems with the merging of galaxies. So, but this leads us to the structure that galaxies need to have this dark matter halo, which extends well beyond what we see. So that was an observation for spherical galaxies, but in elliptical galaxies, we would still expect there was these dark matter be there. Here you see an eye spot. The French-Canadian telescope, Hawaii, gave us this picture of this M87, nice elliptical galaxy. So about 10 to 50% of all galaxies are elliptical. They usually contain old stars, as we have seen, so metal rich. There's not much dust or gas around. they are often surrounded by a large number of globular clusters. So this spherical-shaped satellite galaxies, and they can be quite big. So this one that you see here is, I think, 700,000 light years across. If you remember the Milky Way, the diameter was about 100,000 light years. So much bigger, much more mass. Now, but where do they come from? Well, it's nicely shown here in this video. This video is brilliant. It's a simulation of two galaxies that merge. So like with a couple of billion years, our Milky Way will do with the Andromeda Galaxy. And then the simulation is often stopped, and then the line of sight is changed in order to come to pictures that are basically from the Hubble Space Telescope taken. And here we see nicely basically two galaxies that start to merge. Here the two that approach itself. Here they must have obviously already crossed. And they dance now about a common center of gravity. And this is nicely shown in this video. And then you will see what is the final product. It's a gasless elliptical galaxy. But of course, in this dance, their gas clouds clash onto each other. In this dance, this is another era of absolute star creation. So there, very rich stuff will go on. But then, once the dance is finished, most of the gas has been lost. So not much hydrogen left, not much milk to feed the baby stars, or rather create the baby stars. So enjoy this video, and then I would say, oh, I think we have no halftime. So I will also stop this video and hope that it has been recorded. See you then for the next one.